right, so let's go ahead and date this. Let's see, it's going to be September 15th. So September 15th. And technically we are still in section 1-5, and we're just going to be dealing with more on these infinite limits. All right, now I do want to do some conceptual stuff. We'll do a little bit of problems, a few problems, specific problems for examples, but we're going to take a look at this, and I want you to do a whole lot of thinking today as opposed to just cranking out problems. All right, but let's start with one of the things in your homework. Obviously, they're going to ask you to find vertical asymptotes and find removable discontinuities, and they're going to ask you, go ahead and let Colin let him in, if you will, please. Thank you very much. They're going to ask you to do that, which is not calculus based at all. Those are just practice questions. All right. So if they said something like determine the vertical asymptotes and or removable discontinuities. All right. So again, we're still looking at these things as far as the whether it's continuous, not continuous, what's happening, is there a hole there, is there a vertical asymptote? So again, this is basically more practice of what we've already been doing. This is not calculus, this is just analyzing the function, okay? So they're leading into the limits and how they want you to analyze the function. So if they give you a function like x squared plus 2x minus 8, and then they put that over an x squared minus 4, from pre-calc, can you look at that and tell me what the horizontal asymptotes are? Yeah, pretty quickly, right? We've got an x squared and an x squared, so by our rules, we've got a horizontal asymptote at what? Y equals 1, okay? So not that that necessarily answers the question at all, but do you remember those things from pre-calc? Can you do that? Can you know some things about the function in general? Because that's where I need you to be. We're looking at limits, we're doing things. You've got to be able to mentally picture kind of some things going on with the graph. Okay, now as far as vertical asymptotes, what was the rule last year for finding vertical asymptotes? You set the denominator equal to 0, and then what was the second part that you all forgot? Plug it back in the numerator and see if it made it 0, right? That was what I taught you in pre-calc. Take the denominator, set it equal to 0, or yeah, and solve, and then take that answer and plug it back in the numerator and see if it equals 0. All right, well, why did we do that? Because we threw it out if it equaled 0, right? Okay, so we could do that real quick here. Set that equal to 0, we get plus or minus 2, right? So someone do the math really quick here. So let's say we take 2, plug it back in, so that'd be 4 plus 8 minus 8. Yeah, the negative 2 is fine. The positive 2 is not. The positive 2 makes it 0, so we would have thrown that out, right? Our only vertical asymptote would have been the x equals negative 2, okay? But now think of this from an algebraic standpoint. Can I take that numerator because it's a nice little trinomial, and can I factor it? Thank you very much. I can, right? So let's factor it, x. All right, on the bottom, we know it's an x plus 2x minus 2. All right, so on the top, what am I going to need? A 4 and a 2? Yeah, so a plus 4 and a minus 2. All right, and then from our algebra, pre-calc algebra, I got an x minus 2 and an x minus 2. And what we talked about last week, that action of me algebraically crossing out created a what? A removable discontinuity. Okay, so when we were doing vertical asymptotes last year, and I said set the bottom equal to 0 and solve, and then plug it back in and see if it equals 0 or not, us plugging it back in was algebraically taking care of the factoring and crossing it out. It was letting you know, oh, we got to throw that out because it's not a vertical asymptote. Now we know it's a removable discontinuity, and we know it's a hole. So that right there tells me I have a removable discontinuity at x equals 2, which was part of the questions. It wanted you to find vertical asymptotes and removable discontinuities. Simplifying that function, x plus 4 over x plus 2. After I factor, I cross out, I get down to this, and then hopefully there you can clearly see your vertical asymptote then is going to be x equals -2. So you're taking all the stuff we did in pre-calc, and they're having you review those skills, leading you into the limits, because this is the stuff you got to be thinking about and applying when we start doing these limit questions. Okay. All right, so I don't think we need to do tons more of those. All right, because we've been practicing now for several days for that. Okay, now let's take this and put it and apply it to a limit problem. All right, let's do the limit as x approaches 1 from the left of an x squared minus a 3x all over an x minus 1. Okay, so now we're applying this to a limit problem, but it's a rational function, right? It's a rational function just like the other one. So I want you thinking about, you know, what's going on with this. Do I have any horizontal asymptotes?
No.
No, I don't, right? Because when the top's bigger, right, I don't have any of those. But we had horizontal, we learned vertical asymptotes. We also learned slant. So does it have a slant? When the numerator is exactly 1 more than the denominator, we do have a slant asymptote in there. Okay, so at some point in time, there's going to be a slant. And then how did we find it? We used synthetic division, remember, and we found those. Don't go to that much work, but I do want you thinking that, okay? Oh, okay, so there's going to be a slant asymptote in this somewhere. Okay, now, vertical asymptote. Do I have one of those? X equals 1. Okay, so I know I've got a vertical asymptote at x equals 1. And every time you have a vertical asymptote, what's the graph going to be doing? Either going up or going down close to that asymptote, right? So here's my graph. Here's 1. Here's the vertical asymptote. So whatever this function is doing, it's probably either in here, approaching and going really high here, or maybe coming down really low here, or going up here. The vertical asymptote is there because the graph's going up and getting infinitely close to it. All right, now look at this. This is the part you got to think. They're asking you to find the limit as x approaches 1 from the left. But if you do the algebra first, you know there's a vertical asymptote there. Okay, now if I do a direct substitution, which is that if you just immediately look at that and go, oh, well, I can't factor it, I can't multiply through by the least common denominator, I can't rationalize. So then you're going to jump to that direct substitution, which is good. I want you to do that, but let's see what happens. If I do it, what do I get? I get a 1 squared minus 3 over 1 minus 1, and I get a -2 over 0. Don't let me do my math wrong. So does that tell me anything about the limit?
No.
I mean, you could say does not exist, but we said we didn't like does not exist. Because if I stop and think about, we don't like this as an answer, is it an acceptable answer? Yes, it is. Okay, but you know more. You know there's a vertical asymptote there if you stop to think about it. So then in your mind, you ought to be going, okay, so I need a better answer. I either need negative infinity or I need positive infinity. Yes?
Because it's a -2 over 0, how many is approaching negative?
Ooh, I don't know, is it? That's a good pondering. How can you find out? Does the -2 have any bearing on it or does it not? How am I going to find out? Okay, graphing is cheating. Okay. Putting it in the graphing calculator is cheating. Okay, but yes, we have that tool. So yes, you know what it looks like. Okay. So, but it's a good question that you're pondering. Does the -2 have any bearing on it or does it not because it's in the numerator? I'll let you think about that for a minute. If you didn't have a graphing calculator, although it'd still be rough, what other technique? We've done it algebraically, which we can't. We've done it graphically, then we also can do a numerically. You can do an XY table. Now, without a calculator, it would be rough. I'll give you that. But if you're using the graphing calculator but refusing to hit the graph button, because I want you to get used to using a table of values, my values should what? Approach 1 on the left-hand side, but really infinitely close, and it depends on how, I mean, you could go as far away as 0.5. That's probably not a good idea. All right, but I could do like 0.99. I could do 0.999. All right, 0.9999. I could just keep getting really, really, really close to 1. And then what's happening? And as you do this, these numbers, I think at 0.5 you get 2.5. At 0.7 you get 5.3. I don't know what the rest of these are, but what are they going to start doing? They're going to start getting infinitely big, which does approach positive infinity. In your table, if you were doing the table of values, then you would see that. But there again, it's kind of a double-edged sword. If you had your graphing calculator, why wouldn't you just go look at the graph? The point is, I want you getting used to the table of values. Okay? But it's a lot of thinking, because on a test, you're thinking about so many other things. You're going to do this, you're going to look at this limit, you're going to do that direct substitution, you're going to do this, and then you're going to stop. I just want you one step farther. I want you to analyze the function, maybe write it down, think about it, and then look at what the limit is approaching, and then go, oh, hey, I got a vertical asymptote. And it'll be hard. It'll be hard for you to catch it, especially because you're in test mode. You're just trying to crank out the answers. Yeah. Josiah, did you have a question?
No.
Okay. All right. So in this case, did that negative have any bearing on it? No, it didn't, but it was a good thought. Okay, because you knew it was either going to be positive infinity or negative infinity. Okay. All right. So I definitely want you to look at that.